morning, everyone, and thank you for inviting me for this first climate coffee session. I'm going to start first to introduce a little bit myself. Maybe this is good for people that are just starting with ocean ice, like PhD students, and that are starting their journey in science. So here it is. So I first got introduced with glaciology when I did my master degree at the University of California, Irvine. And directly I decided to start a PhD with Eric Rignot, so in the same university, where I got the chance to study the Greenland and the Antarctic ice sheet, and specifically looking at the vulnerability of glaciers to ocean temperatures using both remote sensing data and a new estimation of bedrock topography. So you have here an example of some pictures of Southeast Greenland glaciers. And this was also the first time I had the chance to go on the field and to go to Greenland. And it was really mind-blowing for me. And that's really the kind of experience that gives you the energy to go forward in this field. So you have here some example of some field campaign that I did in Greenland during the first year of my PhD, which was really a new thing for me. After this, I got a fellowship, a postdoc fellowship from the French Space Agency to go and work in Grenoble at the IG laboratory, where I switched my research interest from the poles to the mountain glaciers, so all glaciers around the world that are located in mountain ranges. And this time I studied the ice flow of glaciers around the world using remote sensing data. And we did a really comprehensive mapping of all glaciers around the world at a high resolution. And here you have an example of ice velocity of the Patagonian ice field from this study. After this, I did 1 year of postdoc position at Copenhagen in the IGN laboratory, and I worked with Anders Bjork. And this time I switched again to the poles, and I got the chance to study the Greenland ice sheet, and specifically the ice shelves that are located in North Greenland. So I'm going to talk a little bit more about this during the remaining of the presentation. And starting in 2023, I got the chance also to join the Ocean Ice Project, and specifically the Work Package 3, and with Gaël Durand. And my task was mainly to make updated estimation of ice shelf freshwater fluxes, so specifically basal melting and iceberg calving. So I'm going to try to take you a little bit through all this experience, and with a focus specifically on ice shelves, both in Greenland and Antarctica. So I know that a lot of people in ocean ice are coming from really different backgrounds. So I wanted to remind you some really general stuff. So we know, everyone knows that glaciers and ice sheets are the main contributors to sea level rise. So there is a really huge need to better constrain their future evolution. And specifically, Antarctica has the largest sea level potential. And what is really specific about Antarctica is that the ice is flowing from the interior of the continent down to the coast, where the glacier starts to float and form ice shelves that you can see here in orange. And these ice shelves are really important because you could see them as giant ice dams that are regulating the amount of ice that is discharged in the ocean. So if these ice shelves get fractured or damaged, it will have a direct impact on the sea level contribution of Antarctica. In the past, we have seen ice shelves that have completely collapsed. So this is the famous example of the Larsen ice shelves that collapsed between January and March 2002. And what we observe is that after this collapse, the glaciers that were buttressed by the ice shelves increased their ice discharge by 4. The ice discharge was multiplied by 4. So there is a real risk, a critical risk for sea level rise if ice shelves around Antarctica gets damaged and weakened. And there has been some large intercomparison model experiment that have tried to model the effect of if every ice shelf in Antarctica would collapse on sea level rise. And this is what you can see on the right. So this is from the ABUMIP project. And what you can see is at time 0, the models have removed all ice shelves, and they have modeled the evolution of the sea level rise contribution from Antarctica. And what you can see is that after 100 years, all the models, the different models represented by the lines, project a multi-meter sea level rise contribution. And recently, there has been some really great papers that have shown that ice shelves are also crucial for ocean circulation. And specifically, there has been these two papers that have shown that meltwater coming from Antarctica has been playing a big role in reducing the overturning in the Southern Ocean. So ice shelf weakening can be caused by numerous processes that happen both at the base, at the surface of the ice, and upstream. And specifically, I got really interested in the processes that are happening below the ice shelf, which is the basal melting processes. And specifically, these basal melting processes can be strongly controlled by the intrusion of circumpolar deep water below ice shelves. And what really plays a role in channelizing this circumpolar deep water below ice shelf is the bathymetry, so the topography of the bedrock on the continental shelf and below the ice shelves. So I got rapidly really involved in trying to understand what is the level of understanding of this bathymetry, because it's a prerequisite for ice shelf and ocean modeling and for future projection. And we know that measuring bathymetry is a really difficult task because in the polar regions, it's really difficult to navigate through chaotic regions with lots of icebergs. You have two examples here with Mogens Fjord in southeast Greenland and of course the Thwaites Glacier, which is really chaotic. And recently there has been some really cool technology based on underwater vehicles that have brought some great data, specifically at Thwaites, Pine Island, and Dodson ice shelf. But those technology are really hard to deploy at the scale of Antarctica. And this is what we need right now in ocean model. So we have came up with an alternative methods to map the bathymetry, which is based on the use of gravity anomaly. And specifically, this is based on the principle that gravity anomalies are proportional to the density of the geological layers below the gravimeter. So basically, if you have a mountain or if you have a trough, it will be directly reflected into the gravity signal. So it's a relatively old method, but it's only recently that it has been used in glaciology to measure bedrock topography. The first example that we have is the one from Michael Studinger in 2003, which measured the shape of the bedrock topography of Lake Vostok in East Antarctica. So the principle of this measurement is that so we are going to use relative gravity measurements. We measure the changes in spring length relative to a reference position. So it's a technology that has the advantage that it can be set up on an airborne platform, so you can measure a gravimetry and invert for bathymetry at large scale and cover bathymetry at regional scale. Yes. So what happens is once we have the gravity signal, we start with, so we are going to do an inversion of this gravity signal to get the bathymetry. And so we are going to start with an initial guess of the bedrock elevation, that is here in pink, and which is constituted of 3 layers: one ice layer with the ice density, the water layer, and the bedrock layer, which is largely dominating over the ice and water density. And what we do is that we simulate the gravity signal from this initial guess, and we are comparing it to the observed gravity. And what we do is that we are iteratively going to modify this initial guess until we have the best fit with observed gravity data. So the first time I started to work with gravity anomaly goes back to 2017, and it was in the Amundsen-Sea embayment, which is the most sensitive area in Antarctica. So what you can see here is a map of the surface flow velocity. In the center, you have the gravity anomalies, and in shaded area, you have the areas that are covered with multibeam. And on the left, you have the bathymetry derived from the gravity. So what we do specifically is that we constrain our inversion with multi-beam data at the front of the shelf and radar and mass conservation reconstruction of the bedrock on grounded ice. And this is key because it ensures a continuity between the open water, the ice shelves, and the grounded ice. And one of the key results of this study was below the dots on ice shelves, which show huge changes in the bathymetry. So what you can see here is a map of the bathymetry from the version of BedMap 2 at that time. So it was basically just an interpolation below Crosson and Dodson Glacier, and the ice was not floating. And what you can see on the right is the gravity-based bathymetry. So you can see this really deep trough that are more than 1,000 meters deep, and with a really interesting connection between Crosson and Dodson ice shelf. So basically, the level of errors that you can reach with this inversion is about 60 meters if you have good constraint, meaning if you have a lot of bathymetry data, if you can also have seismic or AUV data below the shelf. But if you don't have so much constraint, it can reach 100 to 150 meters errors. And recently, I've been working with colleagues at UC Irvine and also at Dresden in Germany, and specifically with Mirko Scheiner, that developed this really cool large-scale gravimetry map of Antarctica at a resolution of 5 kilometers, which is a really amazing product. And we hired a master student, Raphaël Charansin, to provide the first continental scale ice shelf bathymetry map. And what we did is that you can see here the multi-beam coverage, and we also used seal data in areas which is represented here in pink, which allows to give a proxy on the minimum bathymetry at the shelf if you don't have any multi-beam data. And so the results were really, really interesting. So another thing that I didn't mention is that we didn't only invert the data below the shelf, but also on the continental shelf when there was no multi-beam. So what you have here is the example of map on key regions around Antarctica. And I'm going to show you some key profile results of this. So here you have a first example of the Shirazé ice shelves. And what you can see in red is the bed machine bathymetry, and which is a combination of all available multi-beam data and radar data. And you can see first the really big differences below the shelf, but also all along the continental shelf, which is much deeper than what we had before. This is another example for west ice shelves. So basically you can see again bathymetry that is 500 meters deeper than previous bed machine inversions, and you can see that at the continental shelf we have the same solution as bed machine because this is where we have multi-beam data. And here another example in West Antarctica for Abbott ice shelves, where we can see some really deep bathymetry features that goes down to more than 1,000 meters depth. So there is a huge changes around Antarctica, and so we hope that this will be valuable for people working with ocean models, and we are hoping to release this bathymetry product soon, as soon as it will be published, and it will be freely available for everyone. So once now that we got interested in how the warm water can reach and what are the warm water pathways below ice shelves, what is really interesting is how this warm water is melting the ice. And there has been a lot of literature in that concern to try to derive basal melting rates below ice shelves. So what most people are doing is to use ice shelf thickness changes from satellite altimetry data. Because ice shelf, if you have the ice shelf thickness changes, you can isolate the basal melting term if you know the surface mass balance and the ice flow divergence, so from velocity and regional climate model, and the changes in firm air content. So one of the first study to formally derive basal melting rates using that methods was the papers of Rigno et al. In 2013, and it was also the first paper to provide a partitioning between calving and basal melting, and I mean the first to base their basal melting estimation on satellite imagery. So that was the first one of the first estimate between 2007 and 2008, mainly based on eyesight, elevation thickness change. There has been also a lot of really cool study during that year from Pritchard and earlier from De Porter. And about 10 years later, the date is wrong here, there was another study from Atsumili that made another step in understanding basal melting rates, and they provided changes in basal melting rates between 1994 and 2017. And this is what you can see on the map. On the map, you have the total meltwater flux evolution of Antarctica. And basically what they show is that the basal melting rates peaked in 2009 after going back to their steady state value. And more recently, we had another study from Paolo 2023 that also came to the same conclusion, but that extended a little bit their time series. So within the Ocean Ice project, one of my tasks was to provide these updated freshwater fluxes from the most recent studies that are also made available for all the people working in Ocean Ice. But the problem is that those estimations have some limitation. First, in terms of spatial resolution. So what you can see here, you have two GIFs that are the evolution of the basal melting rates from Paolo 2023. And on the right, you have two different estimates, first over Pine Island on the left and for Dodson on the right. And for Pine Island, you have an estimate based on photogrammetry data, which is from David Shin, 2018. And what you can see directly is the big difference in spatial pattern of basal melting rates. In Paolo, you have a much coarser resolution with a really high basal melting at the front of the shelf, which is a bit counterintuitive with what we would expect from the mode of melting of this type of glaciers. And for Dodson Glacier, we can see that the estimate, so this is estimate from Noël Gourmelin, we can see that there is there is a really local basal melt channel that cannot be captured by this coarse resolution data from Paolo. Now, if we start looking at the temporal evolution, so what you can see at the bottom is for the two glaciers, you have the temporal evolution of the basal melting in blue, and this is the calving in yellow, but we are not going to check this out. But for the basal melting, we can see that after 2007, the basal melting significantly decreased, both for Pine Island and for Dodson. But what we see from in situ measurement is that, in fact, basal melting rate should have peaked in 2009 for both ice shelves. And we can see that even for Dodson, the basal meltwater flux increased from 20 to almost 80 gigatons per year. Now, if we look at for the ice shelves in the Amundsen Sea, the comparison of average total basal melt flux, we can see that we can have some really large differences specifically for Corazon, Thwaites, and Pine Island. So there is strong limitation in spatial resolution to accurately quantify the spatial variation in basal melting rates. And specifically, what we have is that those studies are considering a fixed grounding line position, which can affect the long-term trends in basal melting rates, because we are missing, for example, the areas where the grounding line has retreated and where the melt is the highest. So there is a real need to consider ice shelves evolution as a full dynamic object when we quantify this basal melting product. And I wanted to give you a little example of what I am thinking here with a work that I did in North Greenland ice shelves, where we tried to get this approach. So basically, we are studying the last remaining ice shelves of Greenland that are shown here in red. And what we did is that we tried to provide a really comprehensive view of ice shelf changes. So basically, first, we derived the changes in ice shelf area, so looking at the front on satellite imagery, but also grounding lines from SAR interferometry between the 90s and present. Then we quantify ice shelf volume, and here we try to get the best spatially resolved product. So we used NASA Aster DEMs that we reconstructing between 2002 and present, and also worldview imagery. And we calibrated and aligned all those DEMs using altimetry data. Then, of course, what is really important is to account for the temporal changes in surface flow velocity, specifically over these areas that have dramatically changed over the past years. So we use both radar and optical imagery throughout the entire time period. Then we used, for the surface mass balance, we used the MAR regional atmospheric climate model. And we also use ocean temperature to make some comparison with our basal melting results. And of course, basal melting is made by combining dynamically the evolution of the surface flow velocity, the changes in ice shelf area, changes in thickness at high resolution, and the regional climate model. So I'm going to show you a few results here. So here you have the thickness changes of all the remaining ice shelves in North Greenland. So you can see that there is, at the grounding line, changes in thicknesses that are several hundreds of meters. The largest changes that we observe is for Ryder Glacier. You can see that here. And for Stinsby, we have an ice shelf that almost that has collapsed almost completely in 2014. And I didn't see that stayed in French. Then what you can see here is the evolution of the ice frontal position for all ice shelves. You even have the one that collapsed at the bottom, and this is Storströmmen. I'm not going to talk about Storströmmen because it's a specific case. It's a surge type glacier. But for those one, we can see the changes in grounding line. We have monitored large changes in grounding line position, and the most dramatic ones are for Petermann and for Ryder Glacier, where we have a 7-kilometer grounding line retreat in the center of Petermann. And for Ryder, we have a grounding line retreat of 9 kilometers here in the center. Again, this is between the 90s and present. Now, if we combine the changes in ice shelf area with the changes in thicknesses, you can reconstruct the change in volume. And we can see that between the 80s and 2011, ice shelves have lost about more than a third of their ice masses. And what is really interesting is that the volume stabilized after 2011. But the ice shelf continued to thin. And this is because of the grounding line retreat that we observed that increased the ice shelf area. And also some ice shelves have also advanced their ice front. So, and you can see the area that is increasing over that time period. Now, if we combine all of this product with the MAR climate model, we can reconstruct basal melting rates. So here you have average map of basal melting between 2000 and present for Petermann and Ryder at a resolution that is about 100 meters. And we could monitor the evolution in basal melting rate at really fine temporal scale. So what you can see here is the evolution along the flow line of the ice shelves and average across the width of the glacier. And we can see here on the top the evolution of the melt with respect to the draft, and here that's the evolution of the melt with the grounding line, specifically at the grounding line here. So we can see this really impressive increase in melting for Petermann with a peak around 2016. For 79 North, we can see also at the grounding line this really large increase in melting rates that is consistent, that is occurring between 2011 and 2020, most of it. For Ryder Glacier, we observe the same thing at the grounding line here, We can see really on the ice shelf draft, like what is the depth, the ice shelf depth that is most affected by these melting rates. And this is for Stinsby, and we also have a peak around 2014 when the ice shelf collapsed. What we also did now is to try to see if those basal melting rates were consistent with what we can observe inside the ocean. And what we did is that we use a combination of CTD measurements that goes back to the 1960s from the Hadley Center, and we used those CTD measurements to calibrate an Arctic Ocean physics reanalysis from the Copernicus Marine Services in those two regions where we have our interested ice shelves. And so we try to compare evolution of melting rates with evolution of ice dynamics and ocean conditions. So you have here, this is a synthetic figures, and what you can see in the background is the evolution of the ice discharge, the percentage evolution in ice discharge. What you have in blue is the potential temperature evolution. So we have average the potential temperature between 200 and 700 meters. That was based on CTD profiles. And what you can see in dotted black line is the evolution of the melting rates. And we can see that there is a really nice correlation between the evolutions in the melting rates and the evolution of the temperature, with that both peaked around 2015. So which gives more confidence in this basal melting product. So that's it. This is some quick conclusion. So we know that representing basal melting rates in models is a challenge, and specifically due to the lack of observation to constrain models. The use of multiple sensor satellite methods allows us to make significant progress on this, and specifically to unravel bathymetry mapping at large scale. And I think that airborne gravimetry data really allow the paradigm shift for this matter. There is also a real increase in the availability of satellite altimetry at large scale, which was a real milestone for looking at the evolution of basal melting rates, and for use also in calibrating and comparing spatial pattern with ocean model. But there is some limitation that are still persisting in this product. We have seen that it's difficult to have comprehensive product that have a sufficient spatial resolution to resolve small-scale basal melting channel, which can have a big impact on the ice shelf stability. And we have also seen that there can be some disagreement between this basal melting product and in situ observation of melt. So there is still a need, and there is still an effort to be made for getting higher resolution product with ice shelves that dynamically evolve through times. And this is one part of the work that we are trying to do at IGE, and trying to expand what we have done in Greenland for Antarctica. And that's it.